Okay, hi everyone. Today we're going to talk about differential equations. My apologies for having to pre-record this lecture. Differential equations, basically since Newton, mankind has come to realize that the laws of physics are best expressed as in the language of differential equations. Differential equations are pervasive in functions, in physics, in chemistry, and in basically all of the natural sciences and social sciences too. There are a lot of applications for these things. Differential equations relate functions and their derivatives. They're all over the place, and their applications are manifold. They're vast. Okay, this is going to be an incomplete classification of the types of equations we're going to look at. Right? There's the classification according to the order of the differential equations, and this refers to the first derivative of the function. Right? So the leading order derivative. So this is an example of a first order derivative because the derivative is only in the first order in x. Right? Second order or higher can be any combination wherein the highest order determines the order of the equation. Right? So this one is going to be a second order equation because there's a second derivative, and we don't really care about the other ones here. There's linear versus nonlinear differential equations, and what that means is that the dependent variable and the derivatives appear linearly. So for example, this is going to be a linear equation because this term is by itself. This term, even though it multiplies by a function of the independent variable x in this case, it's not y, right? So if it was y dy by dx, then it wouldn't count, right? Here, similarly, and over here, that's all still fine. This is still considered a linear equation, right? Nonlinearity in this case means some kind of multiple of the dependent variable, the y, in this case, y of x. So in this case, it's squared, and therefore it's not a linear one. Homogeneous versus non, what that has to do with is the right-hand side, which is well, it doesn't have to be a constant. Anything that depends on the dependent or the independent variable will break that homogeneity. So this one is considered homogeneous because there's 0 on the other side. Non-homogeneous includes some function. Maybe that function is 0, right? Anything but 0. Maybe that function is a constant or anything like that that has some kind of dependence on the independent variable here. Okay. Initial versus boundary value problems. This is probably going to be the most important for the next 2 weeks because we're going to split up and talk about, first of all, initial value problems and then boundary value problems. Okay, so initial value problems, the solution is determined by the value of the function and its derivative at a single point. So basically what this is typically time stepping problems, right? We're going to have some kind of initial condition like this, y at time is equal to 0, and then we're going to say, okay, the rate of change of y is some function like that. We're going to see a lot of that one. This is not written in terms of time because technically this doesn't have to be time. We're going to get to something called the shooting method next week that's going to talk about this in more detail. Boundary values are probably the ones that you're a bit more familiar with through COMSOL, for example. It's a bit more of a familiar term. The idea there is that you're defining your boundaries on either side, right? So you've got y at some function on one side, y at some function on the other side, and now you're trying to determine that in between. Right? So it's all about starting off somewhere and moving forward, or having like brackets on both sides. I shouldn't use the term brackets. Having endpoints on both sides and then solving for what's going on in the middle. There are ordinary versus partial differential equations, right? The ordinary ones are the ones that only include a single variable and their derivative, right? So a single dependent variable, y in this case dy by dx, and its derivative, that's fine. Partials, of course, include other independent coordinates such as x, space, t, time, right? And then you can mix this stuff. We'll get into this one at the end of this week when we talk about partial differential equations. Finally, time-dependent PDEs. This is going to get a bit more advanced. It probably calls back a bit to your experience with COMSOL at this point. Elliptic PDEs are effectively ones which are only spatially dependent and not time-dependent. So anything that's kind of quasi-static, a lot of elasticity, for example, is a very common elliptic PDE. The parabolic is stuff like diffusion. heat transport, mass transport, things like that have one derivative in time, two derivatives in space, right? That's the key point is the time derivative. And then you have your hyperbolic PDEs, which are your wave equations. So anything that has kind of this acceleration, right? That's when you start to get into these waves, and we're going to have to deal with them separately. Spoiler alert, everything that we're going to derive is actually going to relate back to parabolic PDEs. And what we're going to do is we're going to split them up. And you've probably already encountered this trick where you can say that the second time derivative is equal to a new variable, which is actually time derivative of the other one. And we'll get to that one in due time. Okay, so initial value problems are characterized by knowledge about a boundary condition only on one side of the domain. Typically, these are for time-dependent equations, right? So in this case, your one side of the domain is your initial condition, right? So this is kind of the common one, and here I decided to move this back from x being the independent variable to t because it kind of makes a bit more sense when we're talking about this sort of thing. But if you see it kind of flitting back and forth, the computer doesn't care, math doesn't care if it's time or space or what. It's all just coordinates to it. Okay, so quintessential example for this one is going to be dy by dx is equal to y, and you know some kind of initial condition. That's your boundary term, right? But it's boundary in time, so we call it initial condition. Okay. Similarly, we could talk about something like acceleration, gravitation. We could talk about your original position, the original velocity, no problem. The magic is that we're forced to start at this kind of initial condition time zero and step forward until we reach our goal. And that has a few implications. First of all, error in the solution tends to accumulate with successive steps. We talked about this a little bit with integration, right? Because the integration over each different domain then gets added together in order to form the full domain. Well, guess what? A lot of this time stepping is called time integration because what you're doing is you're taking from one step and you're integrating everything over time to get to the next one, right? So it's not just analogous, analogous, excuse me. It is precisely the exact same context that we talked about in integration. Okay. Numerical noise tends to destabilize the solution scheme. This is going to get us into something called stability and robustness of these techniques, and that actually throws in a lot of curveballs. But we're going to get into that one probably later in the week. Time stepping has to resolve the time scale of the physics that we're looking at, right? This is kind of a bit of a topic that goes back into the computational multiphysics group, but this is that the magic is that, and it's kind of obvious to think about it. Your time stepper has to be able to resolve whatever physics you're interested in. So if you have something like, let's go back to elasticity, right? Quasi-static elasticity, you have some cup and you hit it with something, right? And it produces a strain, and that strain gets balanced out throughout that cup, right? And we're interested in the strain, so we can do something like a quasi-static, right? But we know that acoustic propagation and vibrations are not quasi-static. They are waves. They do transport there, but it's not physics that we're interested in, right? So that's why we can kind of skip over those steps. Careful, careful, careful. Stability is going to come in and kick you in the teeth, right? But in general, we can kind of ignore that because we don't care about that. But we have to be really careful when we talk about that. The time scale may change mid-problem, which is a big surprise when it happens. But on the same side, we also build up a history of the steps as we go. That's going to come in handy when we talk about something called multi-step methods. I think that's under the implicit method, so that will be on Thursday. We'll talk about that one. Okay. Yeah, we talked about this. I alluded to it a little bit. On a high level, we're going to obtain solutions by integrating the differential equation up to a point of interest, right? And so this is why they're called time integrators. Okay. And I already alluded to this one. There's the local truncation error because we're only integrating that time step over, well, we're going to be resorting to Taylor expansions again. Taylor series are infinite. We're not going to do infinite work, right? Therefore, we're truncating. So there's this local truncation error associated with each individual time step. And then there's also the global one, which propagates everything forward and forward and forward. And then we're going to talk get into stability and stiffness, which will be the bane of your existence. I'm telling you right now. Um, we're going to use Taylor expansions. I guess I'm getting ahead of myself here. I'm just so excited about it. Um, as we encountered before, using Taylor expansions, the name of the game is going to be to approximate the higher order derivatives so that we can eliminate the error that those things include, right? There are going to be two classes of methods that we're going to consider. Typically, there's, well, I shouldn't say typically. Single step methods is a little bit of a misnomer. It is what the idea is that you're going to use information about the current time step and not your history of time steps. Okay. So if you're going through and you're doing 10 seconds, you do 1, 2, 3, 4, 5, you're looking for 6, you're going to calculate 6 based on 5 and 5 alone. You're not going to look at 4, 3, 2, 1. Right? The multi-step methods, again, we'll get into later, do consider that history, but single step methods consider only that step. Now, that being said, the way that we achieve high accuracy is by taking sub-steps. So if we were going from 5 to 6, we're actually going to end up going to like 5.1, 5.2, 5.3, 5.5, and kind of building it up there, but they're still considered single steps, which is there's considered single step method, which is again a bit confusing. Um, and then there's the idea of the multi-step methods, and that is going to use that history. But there are actually few applications where that's actually worthwhile. We'll come to that one. Okay, let's see the time here. Yeah, so explicit methods take the information up to and including the current solution in order to predict the next step. Okay, so it's explicit because the future is predicted by the present only, right? Um, bear with me, trust me, and we'll come back to that one on Thursday and I'll show you the alternative. Um, we are looking forward in time. The alternative to look is actually backwards in time. And there are a lot of reasons why you want to do that. But again, that's Thursday's lecture. Okay. Range kata is the go-to in this case. Just like Newton codes defined a whole family of methods, Range kata does so similarly. Um, What we're going to do is take the current time step and we're going to estimate its slope, and we're going to increase the accuracy by approximating higher order derivatives. Okay. Um, the idea is that since we don't have higher order information, what we can do is take kind of like sub steps and then combine them in funny ways to approximate those and eliminate them right off the bat. Now, um, what was this one? Since our time step, our independent variable will be t, right? For t for time. But since we'll be discretizing in time, yeah, what we're going to do is we're going to generate different times. We're going to generate lists of times, right? So t 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we're going to have solutions y at T1, Y at T2, Y at T3, but I got tired of putting brackets and I don't think that's very useful. So instead, we're just going to use this notation where Y sub I refers to whatever time step is also indexed like that. Okay. For first order in time equations, which will include parabolic equations, we're going to find that out soon, right? What we're going to have in general is some function that's going to look like this. dy by dt is equal to a something. Okay, this of course is the slope, it's the time. I tried to make it a little bit concise using this prime notation. Hopefully it'll be clear. But in general, what you're going to have is some function of time and the current solution, right? T and y. Consider now the Taylor expansion for the next time step. So this is y at t is equal to t plus 1, right? But we're just going to use the notation I plus 1. And this is going to be equal to, this shouldn't come as any surprises, the current one plus the rate of change times h, which is now your time step, corrected by the second derivative times h squared, by the third derivative times h cubed, blah, 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 blah. Okay, you put in this equation, you plug in this guy, and what it gets out to is this one now. You've got your current time step, you've got your equation, which excludes the time stepping part, the dy by dt. You've separated that out. Okay, you've got your time step there, and then if you had this derivative, then you could put it in like that, and you would already be eliminating these higher order terms. In general, of course, you don't. So what we're going to do is we're going to represent everything over here, everything on this side, by this sum. And we're going to talk about what exactly the sum is when we talk about the generalized Runge-Kutta method. Okay. Um, these A coefficients here are sets of constants. Okay. K is the function that's evaluated at different positions, different substeps within that interval. And the whole point is that we're going to approximate this sum. We're going to make this sum, approximate all of these terms that fall out of that right-hand side. Everything over here, we're going to try and approximate by this. Okay. It gets a little bit funny. I'm going to tell you right now, Runge-Kutta is a little bit intimidating because it there's a lot of notation. There's a lot of constants that are just kind of floating around. And honestly, like people figure these constants out, and without exaggeration, it's something like one of the constants is going to be 1,753 divided by 12,972. Like it's just kind of like seemingly random, but like somebody derived this stuff. Anyway, I'm going to show you the method. I would never, for example, ask you to repeat what the fourth order Runge-Kutta method, the coefficients of blah, 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 blah. Like this is Wikipedia level, right? Like you would never need to know that off the top of your head. What you would need to know is why these guys are working, how they are working, and what tool to use and when to use it. That's the sort of thing that I want to communicate with you guys. Okay. The forward Euler method is the first order Runge-Kutta method. It has other names. It's also the Euler-Cauchy, point slope method, explicit Euler. Okay, it's going to be the simplest one, and it's quite literally, right? We have dy by dt is equal to some function, and the next time step is the current solution, plus whatever your change is, right? It's super straightforward. It is exactly the left Riemann sum, and we already studied that. We know that its local error, right, for a single interval is OH squared. And when we sum that, we end up summing some factor of 1 over h, because you take the total interval, you divide by the step size, blah, 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 blah. That works out to be a total accumulated error of order h over the entire solution, which is not great. Obviously, there's going to be more that we can do about this. It turns out on Thursday, we'll talk about actually this is terrible. Terrible, terrible, terrible. Okay. Wen's method, probably mispronouncing their name. Wen's method says that, okay, now you have, right? So think back to the way that we did integration, right? We determined that the left Riemann sum was actually a bad approach, right? What we want is to have, so was the right, right? The right one was also terrible. The good ones were the trapezoid rules and the midpoint rules. The thing is there that you don't have, because you're doing a time step, you don't have the next piece of information. There you had like tabulated data, so you had it ready, you could take it, you could use it. Now you're not so lucky. But if you use something like explicit Euler to get your next guess, right? Y at t n plus 1, y I plus 1, can we use that prediction to obtain either some midpoint interpretation or some trapezoid interpretation, and then improve ourselves? This approach is called a predictor corrector approach, right? And it kind of outlines this algorithm, okay? So consider that you have this equation. We're going to make a prediction, y I plus 1 not, right? We're just going to say it's equal to that. And now what we're going to do, we're going to get that. But then what we're going to do is we're going to average the original slope that we calculated, y primed, and the slope that we would calculate at that time step. Okay, so we've started off at our initial condition, we've calculated a slope. We take a time step, we now find our new solution, right? Find the slope associated with that solution. Take the solution, take the rate associated with the slope associated with this solution, and we're averaging them. This smells like trapezoid rule, right? Wrong. Kind of, but not actually. It actually turns out to be pretty different. But then the idea is that you're going to use that average as kind of some kind of approximation of your midpoint, right? And then get your true prediction of the next time step. Okay, so you've made your prediction, you've calculated your correction, and then you've made your better one afterwards. It turns out to look something like this. Okay, so what we've got, this is our slope, which is the differential equation, the right-hand side. dy by dt is equal to f of ti yi, right? And then we're going to combine that and blend that with this solution over at the new time step. Oh, this should be ti, not ti plus 1, not xi. This should be ti plus 1 and whatever solution we guessed, we predicted in that first iteration over there. We're going to average it. We're going to use that to calculate our new and better solution. Okay. The interesting thing about this, and some of you might say, well, gee, if I made a prediction and I corrected that, maybe I could use that as a prediction and make another correction, and use that as a prediction and make that another correction, and I could get arbitrary accuracy, right? Thus solving all problems forever, right? No, not at all. Unfortunately, not so simple. Um, Wen's method with multiple predictor corrector cycles. So let's try and integrate a real problem. We've got something like that. We've got our initial condition here. This is a template code for how Wen's method is being described. So I just want to hammer this guy home. You're going to be given some kind of differential equation. dy by dt is equal to something, right? In this case, this is x, right? I did warn you. This is your f function here. Your f function is not moving everything over to the other side. It's not the same as residual, okay? Your f is whatever your rate of change is. You define your Wen's method, right? And then you can go through your iteration, you make your prediction, you make your correction, and if you want, if you tell it to, then it'll do more and more and more iterations on there. Okay. When we do this using a single iteration, so we're only going predictor and that's it, right? We're not even circling back. Nope, never mind. We do that once. We do predictor, corrector, and out. Okay. What we're going to get is the first time approximation is this, right? Our true value is, not bad, right? Second time is this. True value is, okay, that's kind of different. And at time 4, we've got 83 compared to 75. If you can't make that out. Okay, now we're going to compare that, and we're going to compare that to a case where we're actually going through that cycle, that iteration cycle, predictor, corrector, 15 times. Okay, and what you're going to see, that's where this code comes in. What you're going to see is that yes, we do converge on an answer, but it's not the right answer, right? So the predictor corrector finds a something, and it does actually converge on that something, but it doesn't actually converge on the right thing, which is a problem, right? And this is kind of indicative. So even at time 4, originally we had something on the order of 80. This does bring it down to 77, but the answer is still 75. So we haven't actually achieved arbitrary accuracy. All we've done is we've converged on a solution which is not the correct solution, which is unfortunate. Welcome to numerical methods. Um, in the special case, so what can we do, right? In the special case where the slope doesn't depend on the function value. So this is a very easy differential equation where you have something like dy by dt is equal to some function of t, right? Not y. Then the predictor can be calculated directly. You eliminate the cycle, and lo and behold, what you end up with is the trapezoid rule. Okay, but this is not a very useful case because we have more tacked onto there. If we could use it, of course, this would have order h cubed locally and order h squared globally. Okay, now here's the magic. Okay, we're going to talk about the midpoint method, which in this case, right? Remember that an integration midpoint method was a very useful approach. Okay, is it midpoint or yeah, no, it's midpoint method. Okay, what we're going to do is, and we found out that this was, we kind of use the midpoint to kind of cancel out the above and below error, right? It comes out to the same kind of idea. So in this case, we're going to start off at yi, and we're going to take a half step. So we're going to call that yi 0.5, right? And we're going to take that value evaluated at the initial condition, but only h over 2. And then we're going to take the slope at the half step and the solution of the half step, and we're going to use that to calculate the whole step. So we're not blending in that information, right? Sorry, we're using that to get to take that whole thing. Okay, so we get the total step is the initial step plus the slope in the middle over the whole step. We haven't blended anything. We've used that half step. We've used that to calculate the slope in the middle of the interval. Sorry if I was confusing there. And then we're using that value to take the whole step. And this actually works out to have order h cubed, local order error, and order h squared global, which is good, which is already a lot better for the cost of taking one step in the middle. Okay, this is interesting because it implies that we can calculate and combine substeps to effectively achieve better predictions, right? So the name of the game from henceforth is going to be, what kind of substeps do we take? Do we blend them? This is a case where we didn't blend them. If we do blend them, then can we gain some kind of benefit from it? What else can we exploit in order to get this? And this is going to take us into, okay, we're back. Now what we did so far was talk about the midpoint method. We kind of struck on this idea that you could take information from this half step, blend it into the rest of your information, and actually achieve higher order accuracy than you would have normally done. Okay, we're going to take this idea and we're going to generalize it into something called the general Runge-Kutta methods. So if you remember, the whole idea with this one is that we wanted to take the next solution, as a function of the current solution plus this sum of material over here. Okay. For the explicit set of Runge-Kutta methods, the way that this is broken down, an are going to be the constants. That's going to be one set of constants. There's a whole bunch of constants here. An is going to be one set of these constants, and then you have these kn here, which are your slopes, right, at your intermediate time steps. So your subdivided thing, you've taken your substeps, and now you're calculating it at each one of those. Okay. So for example, typically the K1, the slope at the first one would probably be better off labeled K0, but it's labeled 1 for historical reasons, I suppose. Right? That's going to be your slope at your initial time and your initial solution, right? And then your K2 is going to be this half step or partial step. Okay, so P is going to be some fraction, is going to be like P2 or P3 or something like that. Q21 is just a constant. You'll see why it's indexed like that in a second. But so we're going to blend our current solution plus some value, some fraction of this intermediate solution, and we're going to calculate another slope. And then we're going to end up using that to find yet another guess, right? Because we're blending that information here, so on and so forth. Okay, Runge-Kutta methods are going to be determined by their order, and their order corresponds to how many of these lines, these are steps, these are the stages of it, okay, that you're going to go down. So for example, RK1, the first one is just forward Euler, right? There's only so many ways you can start off at the beginning and take a step right to the end. Okay. These are concisely summarized in something called a Butcher tableau. So notice, first of all, you have all these sums of these constants an as you're going, right? Imagine that's going horizontally. You're building up this horizontal line. Now, if you look at these p values here, they're forming a column vector. You've got a row vector, a column vector, and these Q21, 31, 32, right? Like you have two indices, it's going to be a matrix. Okay. When you put that together, you get this concise representation. It's not simple, right? These things are not simple to know
luckily for you, I'm not going to ever ask you which method this is, what these constants are. These constants are not trivial, by the way, too. You'll see on RK45, they're ugly constants, but they're determined and they're standardized, and they're for very good reasons. Those are the go-to. Um, Okay, but this is a nice way to kind of like conceptualize and encapsulate this going into different things. Okay, so notice that the Q matrix here is lower triangular, right? It's okay. It's actually missing the diagonal here, but it is going down. Oh no, sorry, it has the diagonal there. So it is lower triangular in that it doesn't have anything above your diagonal there. Okay. Um, we on Thursday will discuss and introduce the implicit family of RK methods, which turns out to upper triangular. Or you can actually have mixed methods. So if you've ever worked with something called the Crank-Nicholson method of time stepping, that would be considered a mixed method. But at that point, you probably know where I'm going with implicit time stepping anyway. Okay, RK2 methods. So remember that the name of the game is to try and get this summation of characters over here to match your Taylor expansion, your higher order Taylor expansion, insofar as possible. Okay, so for a second order, we're only going to do two orders of our Taylor expansion, and we're only going to limit ourselves to K1 and K2. You write out what these are. I'm not going to go through the math. Feel free. You have the notes here. Um, what you end up getting is an equation that looks like this. Okay, so you've got your next time step is equal to your current, excuse me, your next solution is equal to your current solution plus some combination of terms times your slope plus some other combination of terms times these other guys here. What you're going to do is you're going to compare that against the Taylor expansion. So you look at your Taylor expansion, you bust this out using the chain law, okay, and now you're going to match up your terms. So you look, the coefficients of this guy is a1 plus a2. a1 plus a2 is equal to 1, okay? a2 p2 here is equal to 1/2. Note the 1/2 is buried in the h over 2 here, right? And similarly for a2 q2 1 over here comes out again here. Okay, now we have four unknowns, A1, A2, P2, PQ, Q21, mind your P's and Q's, right? We have four unknowns, but only three equations, which means we're going to have an underdetermined system of equations. We're going to have a single degree of freedom, which we then have to fix. But once fixed, whatever combination of those other unknowns is still going to solve our system. Okay. What that means in this context is that we're going to have one degree of freedom that we're going to be able to choose, but whatever that choice is going to result in an order 2 accurate approximation for these particular time stepping methods, right? We did two of these guys. We talked about Wen's method. And sure enough, when we declare that A2 is equal to 1/2, you follow through the math and you recover Wen's method. Here's the Butcher tableau corresponding to that one, right? Which is order 2 accurate, which we worked on. Or excuse me, order 3 accurate locally, order 2 globally. And we worked out the midpoint method. You set A2 is equal to 1, you do da 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 da. Here's your butcher tableau, and yet again you've again achieved order 3 locally, order 2 globally. Okay. There is also Ralston's method. Ralston's method is for a different choice, and it's actually provably the minimum bound. So this is as good as you're going to get. Everything is order h squared. That constant that I said ignored, turns out there are actually cases where you do want that constant. Ralston's method is the correct answer for this case. Nobody actually does RK2. It's almost always RK4 or even better RK45. We'll get to that one. If you were so inclined to do RK3 because you remember Simpson's rules and you want to get back into that one, this is the template. So what's happened now is that you've got the third order there. Now you've got a third stage there, and the amount of unknowns has increased kind of geometrically, whereas your number of pieces of information, your number of equations has only increased linearly. Right? So now you have more degrees of freedom, more unknowns that you're going to have to set, right? But happily, you've got people who already set it for you. This is kind of the standard RK3. You can follow through here, see how it works. It recovers actually Simpson's 1/3 rule if f is only a function of t. So if f is not a function of your unknown variable, in this case y, then you would recover Simpson's rule. So it's a nice point of contact, right? Locally, order H4, global H3. Butcher tableau is here. RK4 is the common implementation. It's kind of the trade-off where the computational complexity gets into like whether or not it's worth doing that versus taking smaller time steps and things like that. But we'll come back to that one soon. Um, there's also the fact that honestly, when you're getting up to fourth order accurate things, it's kind of diminishing returns at that point. Okay, now you have even more unknowns, right? But happily, you've got Ranjan Kata, I think, who came out with this, and they actually invented the fourth order one and said, okay, guys, this is going to be our go-to. Here is the expression here. Here's this. If you follow through with it, it turns out to be order fifth locally, order fourth globally, and here's the butcher tableau. This is not, maybe it is to you. For me, this is not easy to interpret. I can't look at this and immediately visualize what's happening here. Um, Happily, Wikipedia has a very nice free diagram that I blatantly stole and include here. Thank you, Common Creative Commons. Okay, so this is a pictorial example of, I'm just going to move this over there. I think it's invisible for you guys anyway. Um, Okay, this is a pictorial example of what's happening here. So you're going to start off with your initial guess, which is at t0, y0, and you're going to calculate your slope. That's your k1. Okay, you're going to use k1 to take a full half step, and you're going to calculate what your slope would be if this were, this is your time and this is your initial guess for that half step value. You're going to use that slope, take it back to the beginning, and step all the way over here, right? Now you've got another guess from which you calculate another slope. You take that one and you step all the way out to your full one. Now you've got another time and another guess. You calculate yet another slope, and then you slam them all together, you shake them all together, and sure enough, you get this nice step, which actually, like, it actually finds it very well. It's highly accurate. Um, it's a little bit convoluted how you get to this thing, but the fact that you achieve, like, fourth order accuracy for a global case, fifth order locally, is actually very, very impressive. Um, Notice the way that this is working conceptually. RK4 is walking its way from your initial condition to your final, to the time for that interval. It's taking kind of those small steps along the way, and it's combining that information intelligently so as to cancel out your higher order derivatives and achieve this kind of better overall answer, quantifiably better. Okay. This is going to seem a little bit funny to some of you who are going to be thinking, well, wait a second, why not just take a half step? Why even call it a half step? Just cut your step size in half, right? And then you would be taking small steps. Maybe you could even use something like RK2. In that case, you could use a midpoint rule or something that's a bit easier to calculate, right? The problem is that if you use RK2, you're only accurate to third order locally, and you've got two of those, right? Remember, you've got that order 1 over h, right? So that reduces your total accuracy for that, just this time step, to order h squared, right? And order h squared is much worse than order O4, than order h to the power of 4, right? It's quantifiably better to take a full step than a series of small steps, and that should be a bit disturbing to some of you guys, until you realize that that's actually exactly what RK4 is doing. It's taking those small steps and it's combining them in an intelligent enough way that it's achieving that whole step, while canceling out your uncertainties, your higher order corrections. Okay. Um, but, and there's always a but, um, there is an implicit assumption that your function in this entire interval is behaving not crazily, right? Because if, and you can look at this plot and you can imagine if your curve did something like this and it came up and then sharp drop, right? When you do that extrapolation, you get that sharp drop. It's going to come up with a nightmare, right? Like that slope over here has nothing to do with the slope over here. You blend that, and you're just going to get a mess, right? This is where you might want to adjust the time step itself. This is where we get into adaptive time stepping. There's a whole framework associated with that one, which we're going to start on Thursday.